A matrix is a rectangular array of numbers.
What exactly do you think it is?
Oh, yeah. So whenever we talk about a matrix or you're describing a matrix to somebody, you have to be like, oh, I'm talking about a 2 by 2 matrix or a 2 by 3 matrix, right? Whenever we say blank by blank, we're to always say the number of rows by the number of columns. So like this is a 2 by 2 matrix because it has 2 rows and 2 columns. This matrix over here would be like a 3 by 2 matrix because it has 3 rows and 2 columns of entries. And like this one over here, this would be a 4 by 4 matrix because there's 4 rows and 4 columns. So, size of a matrix is kind of like saying the size of a vector. Remember, the size of a vector is just how many entries are in the vector. When you talk about the size of a matrix, you have to say the number of rows and the number of columns in that order. Yeah, so like what Abdullah is saying is a square matrix is exactly what you think it is. So a square matrix just means that the array is a square. So like this is a square matrix, this is a square matrix, this is a square matrix, but these are not square matrices because for a square matrix, the number of rows is the number of columns. So it looks like a square. Okay. So our next vocabulary word is the determinant. And the determinant is a scalar that you can calculate only for square matrices. So if you have a rectangular matrix and someone asks you for the determinant, say, sorry, you can't take the determinant of a rectangular matrix. It has to be a square matrix specifically if you want to find the determinant. And so sometimes I see these notations. You can either see DET and then the matrix. So DET obviously stands for determinant. Or if you see this where it looks like the absolute value, like instead of square brackets, you just see the vertical bars. This is asking for the determinant of this 2 by 2 matrix. The way you calculate the determinant of a 2 by 2 matrix is like this. We say 2 times 5 minus 3 times 4. Okay? So you multiply the top left and bottom right entries, 2 times 5. And then you subtract the product of the bottom left and top right entries, right? So this is 2 times 5 minus 3 times 4. So my determinant would be 10 minus 12. My determinant of this matrix is negative 2. Okay? Good morning.
Morning.
What's the motivation of calculating the term?
That's such a good question. I really wish that this were the case. I wish that our math education did calculus 1, calculus 2, linear algebra, calculus 3, differential equations. Because linear algebra just makes all of these matrix calculations make so much sense. And there's a lot of good reasons behind like determinants and stuff. But if you skip linear algebra and you go directly to calculus 3, then I have to like make you do all these calculations that don't make very much sense. So the meaning of the determinant in linear algebra is that it is the product of the eigenvalues of a matrix. But if I just tell you that and you don't know what eigenvalues are, I'd have to teach you a whole class in linear algebra before you would know what an eigenvalue is. And so skipping the definition of eigenvalue, because we just don't have time to talk about eigenvalues, determinants don't really mean very much, but again, I have to teach you this so that we can move on with Calculus 3, and we'll use determinants here and there. Like just for one little thing today, we're using the determinant, and then at the very end of the semester, we'll talk about the determinant of the Jacobian matrix, and we'll use that for like one little thing at the end of the semester. And I wish I could give you a more like big picture view of things, but you'll have to wait until linear algebra to really understand why a determinant is even useful.
So I'm just taking what we need from linear algebra.
Yeah. Okay. So, anyways, this is the determinant of a 2x2 matrix. Then, let's do another example just for good measure. If I'm asked to take the determinant of this matrix, -2, 3, 3, -8, this would be -3 times -8 minus 2 times 3. So it would be 24 minus 6. So it would be 18. Okay? So just like before, we're doing the top left and bottom right entries, multiply those, and then we subtract the product of the bottom left and top right. So the determinant is a scalar that you can compute for square matrices. I just showed you how to compute the determinant for a 2x2 matrix, and it's pretty easy. The determinant for a 3x3 matrix is actually annoying. It's really, really long and annoying in my opinion. But here we go, we're going to try it, because we have to do it. If you want to compute the determinant of a 3x3 matrix like this one, 9, 7, -1, -8, -3, 3, -3, -5, 7. It's not very bright. What we have to do is we have to say, I'm going to think about this 9, and then I'm not going to think about these for right now. And then I'm going to look at this 2x2 matrix and take the determinant of that 2x2 matrix. Okay? So, I'll have -3 times 7 minus 3 times -5 as the determinant of that 2x2 submatrix down there. So we do the 9 in the upper left corner, we forget about these numbers that are in the same row, in the same column as the 9, and then we take the determinant of the 2x2 matrix that's left. Okay, then we're moving on. Then we are going to, and this is the crazy part, we're going to subtract the 7 on the top row. So now I'm thinking about this 7. I'm not going to worry about the 9 or that or this. I'm not going to worry about or think about any of the numbers that are in the same row or the same column as the 7. And what I'm going to do now is I'm going to take the determinant of this 2x2 matrix that's left. Okay, so this is going to be 7 times the determinant of -8, 3, -3, 7. Okay, after we're done with this, then we are going to, lastly, we're going to look at this -1 over here, And we're going to add that negative 1, cover up these numbers that are in the same row and the same column as the negative 1, and then we're going to take the determinant of this matrix that's left right here. So this 2 by 2 matrix is like negative 8, negative 3, negative 3, negative 5. Take that determinant. One of the hardest parts for me to remember about this whole procedure is that you have to subtract the middle number of the top row. I don't know why it's so hard for me to remember, but I always just do like 9 times this determinant, 7 times this determinant, plus 1, negative 1 times this determinant, and I forget to subtract the middle one. So this minus sign right here is the one that I'm always going to screw up, and I'm always going to accidentally write a plus sign. But you have to remember that the pattern goes plus, minus, plus. And so you're taking a determinant, and of course we're not done yet. So I have 9 times, negative 3 times 7 is going to be negative 21, minus 3 times negative 5 is going to be plus 15. Okay, minus 7 times, the determinant of this 2 by 2 matrix is going to be negative 8 times 7 minus 3 times negative 3. Plus negative 1, I'll just write minus, times the determinant of this 2 by 2 matrix, which is negative 8 times negative 5 minus negative 3 times negative 3. So that's going to be 9 times negative 6, which is negative 54, minus 7 times negative 56 plus 9 is negative 47 minus 31. So that's going to be minus 85 plus 7 times 47 is 329, yeah. And that is 330 minus 80 would be 250. So 244. Okay. Haha. So like I said, finding the determinant of a 3 by 3 matrix is a huge pain in the butt. If you just want a glimpse of an even more massive pain in the butt, here's a 4 by 4 matrix. What if you wanted to take the determinant of this thing, right? Okay. What you would do is you would say, let me look at this 1, cover up those, and then I'll multiply by the determinant of that 3 by 3 matrix. And then you would say, let me look at the 2, right? You'd say, let me look at this 2, and then cover up those, and I would take the determinant of that 3 by 3 matrix. So remember, a 2 by 2 matrix, that determinant was so easy. But in a 3 by 3 matrix, this determinant required us to take 3 2 by 2 determinants. If you want to take the determinant of a 4 by 4 matrix, you have to do 4 3 by 3 determinants. And so that would end up being the same thing as, let's see, that would be like 12 2 by 2 determinants by the time you were done. And so if you wanted to do a 5 by 5 matrix, that would require you to do 60 2 by 2 determinants, you know. And so this explodes, right? It goes up by sort of like the factorial.
And the same as the 3 by 3, you have to do plus minus plus minus?
Yes, yeah, exactly. So you do plus minus across the top. So determinants are a real pain. What we're going to end up doing in this class is mostly 3 by 3 determinants. which is not fun, but also not impossible. Let's check our work right here. So I want to check my work and make sure I did this determinant correctly. What I'm going to do, what you can do at home, is you can open up Excel. And you can type in your matrix, so 9, 7, -1, -8, -3, 3, -3, -5, 7. So here's my matrix. And if I want to take the determinant, I type in equals M for matrix, determ for determinant, so matrix determinant, and then you have to select a square array, and then it tells you 244. We didn't mess up. We actually did all arithmetic correct, and we didn't make any little mistakes, right? So you can check your work that way.
I did the 4 by 4 on my calculator. It came out with 0.
So determinants can be 0 if one of two things happens. A determinant will be 0 if you have the same column twice. Then that will make a determinant 0. Or another way this can happen is if one column is just a scalar multiple of another column. So like if I multiply the right column by 2, so -1 times 2 is -2, 3 times 2 is 6, 7 times 2 is 14. If one column is just a scalar multiple of another column, you'll get a 0 determinant. And the last thing that can happen that messes this stuff up is if I make this third column just equal to the first column plus the second column, then that's a 0, right? The E -13, that just means it's a really tiny number. That's just round off error because that determinant should be 0. There we go. So since this third column is just the first column plus the second column, that makes the whole matrix determinant 0. If I was teaching a linear algebra class, I would tell you about why that is, and we would learn a little bit about cool and interesting math. But
Like the system of equations.
yeah,
Simplifying
it
the-
is. Yeah, we would call this a dependent system of equations, and so since it's dependent, you end up with a 0 determinant, and yeah. Yep. So anyways, you can check your work with determinants just by doing this in Excel, and like Excel is really good because then you don't have to put in any sort of work or effort on your own part, and even like a 4 by 4 determinant is not that hard to figure out with Excel, right? Not too bad. Also, I want to point out, though, if your matrix is not square, you can't take the determinant. And Microsoft Excel knows this. So if you try to put in some non-square matrix, like this one, it'll give you an error. Okay. I hope we're not going to fall too far behind today. So this is what I'm really trying to get to. It's called the cross product. Yesterday, we talked a lot about the dot product. And the dot product was a way where we multiplied two vectors, and the product was a scalar. The cross product is going to be a way to multiply two vectors where the result is a vector. But the cross product only works for three-dimensional vectors. Only works for three-dimensional vectors. So if you're ever asked to take the cross product of, two-dimensional vectors, say, no, sorry, cross product only works in 3 dimensions. Okay, so the cross product, this is the formula for it. I'll give you a minute to write this down. You really, really, really have to memorize this. Okay. if you have these vectors, u and v, and where I've written the little subscript 1, 2, and 3, these are scalars, right? So I'm just saying that u1 is the first entry in my u vector. That's a scalar. u2 is the second entry, and then u3 is the third entry. Then when I ask you to find the cross product, I want you to write a little 3 by 3 matrix. And across the top row, we write I, j, k. The second row, we're going to write the entries of your u vector, or whatever the first vector is. And then across the bottom row, we're writing the entries of your second vector in the cross product. And then what we're doing is we're going to take the determinant of this little matrix, this 3 by 3 matrix. So
that is the one when j is negative? That one?
yeah, so j is going to have to be negative when we go to take the determinant, because it's going to be plus minus plus.
Oh.
Yeah. And exactly, these I, j, and k are from what we saw before, where I is the 1, 0, 0, j is the 0, 1, 0, and then k is the 0, 0, 1. Okay. So let's see what this looks like to actually do in practice. This u cross v is going to be this determinant of I, j, k, 4, 5, 6, negative 1, 0, 2. So I'm going to have I times the determinant of 5, 6, 0, 2. And Leah's right. I'm going to have to write minus j times the determinant of 4, 6, negative 1, 2. Yeah. And then plus k times the determinant of, perfect, 4, 5, negative 1, and 0. So what is the determinant of 5, 6, 0, 2?
2 times 5 minus 6 times 0.
Yep. So that's going to be 10. Right. 5 times 2 is 10. Minus 0 times 6. So minus 0. 10 minus 0. Okay. What is the determinant of 4, 6, negative 1, 2?
2 times 4 minus 6 times 9.
Yeah, it would be 8 minus 6, which is 2. And then k times...
Plus,
Minus
6.
8 plus 6, because it's 8 minus 6.
Oh, you're right. Yeah. Not bad. Yes. The determinant should be 8 minus negative 6. Okay. Finally, what is the determinant of this 2 by 2 matrix at the end here? Should be positive 5. Remember, 4 times 0
Wait.
minus negative 5. It's 5. Okay. So, like I said, the cross product is a way to multiply two vectors where the result is a vector. So here, my result is going to be 10, negative 14, 5. Because remember, I is the vector 1, 0, 0, j is the vector 0, 1, 0, and k is the vector 0, 0, 1. I skipped a step, maybe I'll just write out this step. So I is 1, 0, 0 times 10. J is 0, 1, 0 times 14. And then k is 0, 0, 1 times 5. So this is going to be 10, 0, 0 plus 0, negative 14, 0 plus 0, 0, 5, which is equal to 10, negative 14, 5. Okay? We could do another example. It probably is important enough to do another example. So we'll do this, and we might not finish 11.4 today, but that's okay. Here's my vector A. Here's my vector B. Let's find A cross B. So A cross B is going to be the determinant of the matrix where I have ijk across the top. Then -5, 1, -3 here. And then 8, -5, 5 across the bottom. So
That doesn't matter if you put -3, 1, and -5. Like reverse it. The row.
does it matter?
Yeah.
Yeah. I think so. I'm like almost certain yes. Yeah. We're going to talk about this in a minute. If you want to swap the rows so that like the middle row is 8, -5, 5, and the last row is -5, 1, -3, you'll get the same thing, but you'll get the negative of it. So, in other words, what I'm trying to say is A cross B is actually negative B cross A. So if you completely interchange the second row and the third row of the matrix, you'll get the right answer, but all of the entries will be negatives. This means that the cross product is not commutative. It's like almost commutative, because if you commute them, it just gives you the negative. We call this property anti-commutative. So we would say the cross product is anti-commutative, because if you commute the factors in the cross product, then you get the negative. So this would be anti-commutative. Okay. Anyways, we have I times the determinant of 1, -3, -5, 5. Remember, minus j, because the pattern here that we have to remember for determinants is plus, minus, plus. So then we have minus j times the determinant of, what is in this matrix right here? Perfect, yeah. Very good. And then k times the determinant of
-5, 1, and
perfect. Okay. So I have I times, what is this determinant? -10, very good. Minus j times, what is this determinant? I have to think about it. So -25 minus -24. So yeah, -1, perfect. And then this determinant is 17. Okay. So then our resulting vector is going to be the vector -10, 1, 17. Okay? We got it. All right. Very good. All right, so, oh, here's a big typo. That is the cross product. So the cross product has the following properties. Remember, it is not commutative, it is anti-commutative. But the cross product is still distributive, it's still associative. If you cross a vector with the 0 vector, then your result is the 0 vector. If you cross a vector with itself, the result is the 0 vector. So any vector cross itself is the 0 vector. Like if you have 1, 2, 3, cross 1, 2, 3, the result is 0, 0, 0. Okay? That's kind of important. Another super important one of these properties is this one. It says u cross v is orthogonal to both u and v. So that's very, very, very important to memorize. That has to be written down in your notes somewhere. A way of thinking about this, since u and v have to be three-dimensional vectors, like if you point with your index finger, right, and then you extend your middle finger so that it's at a 90-degree angle, okay, like this, that would be like a u and a v vector. These are orthogonal to each other because you see the 90-degree angle. Another orthogonal vector would be like if I extended my thumb, right? And so these are orthogonal to each other, and my thumb is orthogonal to both my index finger and my middle finger. So in 3D space, that's how you can end up with three vectors that are all orthogonal to each other.
So I, J, and K are same thing?
Yeah. Yeah, you can think of like I, J, K. And then again, this would be like u, v. U cross v has to be orthogonal to both u and v. Okay. This is a formula that should look suspiciously familiar to you. I'll write this over here. Sine of theta is equal to u cross v over u norm v norm. But you also have to take the norm of the numerator. So again, this should look really familiar because yesterday we talked this to death. U dot v over u norm v norm. That is what gave us cosine of theta. So if we replace the dot product with the cross product, we'd be in a situation where we had a vector. And so to get rid of the vector, we have to take the norm of the numerator, so that gives us a scalar, and then we equate that to sine instead of cosine. So that's a way you can keep track of both of those formulas. This next fact is pretty important. U cross v is 0 if and only if u and v are parallel. Okay. So if you have two vectors that are parallel, meaning they're like the same direction, then their cross product is going to be 0. And if someone tells you that the cross product of two vectors is 0, that automatically tells you that those vectors must be parallel. Okay, and then this last fact is also pretty important to have in your notes. Everything I've circled here is important to have in your notes. But this last fact, this last statement says that the norm of the cross product is the area of a parallelogram where the vectors make up the sides of the parallelogram. Okay? So, what do I mean by that? If this is my vector u, this is my vector v, I can make a parallelogram by sliding a copy of my vector v over like this, and slide a copy of u over like this. Okay? So this is a parallelogram with sides u and v. The area of this parallelogram is the norm of u cross v. The actual vector, u cross v, is a vector that's orthogonal to u and orthogonal to v. So this would be like u cross v over here. But if you were only taking the magnitude, or you're only taking the norm of that vector, it would actually give you the area of this parallelogram. So that, if you can remember that the norm of the cross product is the area of the parallelogram, and you also know that u and v are parallel, so u and v are pointing in the same direction, well then that parallelogram is going to have 0 area. So that's why we say if the cross product is 0, then the vectors are parallel. Also, if the cross product is 0, then sine of theta must be 0, so theta must be 0, so the vectors must be parallel. Yeah.